Okay, so this is a cool week. We're going to do something called vectors, and this is not only a pre-cal topic, but it's also a physics topic. So you're kind of getting a 2-for-1 out of this, where you're going to see it in both classes, and it's going to help you out for both classes. Now, this is probably going to be a long video. I'll apologize in advance, but I'm kind of cramming like a 2-week unit into one lesson. So I can't get into every little thing, but I'm going to try to touch on every little thing just so you feel comfortable with it when you're in the classroom, okay? So first of all, let's talk about what is a vector. And I know it was in that Disney movie, what was it, Despicable Me, that was the villain's name. And in fact, he had a line where he says, I have both magnitude and direction. And a lot of people probably didn't get that, but if you watch it again, you'll get a kick out of it after this lesson. I know all the nerdy parents laughed in the theater when I went to see it. So anyways, a vector is anything that has both magnitude and direction. Now, you might be wondering, like, okay, so what does that mean? Basically, I'm drawing it here as an arrow. Like, I want you to imagine that it's it's not physically going to be an arrow like in space, but think of something like, okay, let's think about like a car driving, okay? If you're looking at a car driving and you're looking at that aerial of a car driving, then it has a specific direction that it's going, like north, south, east, or west. And it also has a magnitude, meaning the speed that it's traveling at could be its magnitude, okay? If it's a physical arrow, and we can actually describe it that way, where we draw an actual length, then the magnitude of the vector could just be the length, okay? The length of the vector. So if it's just a picture, like just a two-dimensional picture, it's going to be the length of the vector. If this is real world, it can be all kinds of stuff, but a lot of times it really does represent speed of the vector. And you're also going to do problems that involve force and work, and there's just all different kinds of things in physics. But for math, mostly you do speed. Okay, so that is the magnitude of the vector. It also gets a special notation or label. So over here, if this is vector A, okay, the way that magnitude is often denoted is it looks like it's in absolute value bars. So if you were to see this symbol right here, that would just be asking you for the magnitude, okay, or the length. So not too terrible, right? Okay, so the direction of a vector is going to be just that. When I mentioned like north, south, east, and west, well, that's it. How is it going? And usually whenever you measure direction, it's going to be the angle measured from a horizontal. I'm going to put from the horizontal. And sometimes it's already attached to a horizontal. Like if you look at my picture over here, I have one A that's drawn up here, and I have another A that's drawn down here. This one's already attached to a horizontal, so the direction of this one you could just label as a theta. But if you left it out here in the middle of nowhere, you would need to draw your own horizontal and measure that as the direction, okay? Now, there's other parts of a vector, and so that's what this section is going to be, parts of a vector and naming it, okay? So the parts are pretty much this. You already know magnitude, that's the length. You already know direction, and that's just the angle. The point where the vector starts, okay, is called the initial point, and in fact, I'm just going to label these. I'm going to put on an extra BC just so you can see what I'm talking about. Point B would be the initial point, because that's where the vector has started from, and so point C would be called the terminal point, because that is where the vector is ending, terminal end, right? For shortcut, sometimes teachers like to call this the tail of the vector and this the head. I am very guilty of that. So throughout this video, you're going to hear me using these words interchangeable. I like head and tail because they're fast, and it makes sense because the head is where I draw the arrowhead, okay? So you'll hear me saying both. Now, naming a vector, there's a couple of ways to name a vector. Sometimes you will just see vector A, and they will just like literally write vector A, and a lot of times I see it in capitals or bold. I see a lot of bold in the book, but that's how they'll do a vector. Sometimes you can name a vector by 2 points, and that's what a lot of people do at first. Like this one up here, this instead of vector A, we could also call it vector BC, because we're naming it by its ray or segment that goes with it. And the thing is, you do need a notation up here. Now above this I'm going to draw, it's going to look familiar from geometry. It looks like the symbol for a ray, but notice I did not finish the arrowhead. And the reason for that, guys, is that this is not a ray. It doesn't keep going forever. That arrowhead is where it stops. The arrowhead is only there to show you which direction it's traveling in. So if I say vector BC, I do this symbol that's like a half arrow, but when I read it, I know that since C is under the half arrowhead, that must be the terminal point, and that must be the initial point because it's under the tail. And so that's another way to name a vector. Now, you're also going to see notation with vectors where, I guess let me see, I think what I want to talk about next is going to be shifting the vector. So this is going to be an important thing because vectors, what's cool is, and the reason I've drawn 2 A's up here is to show you that this vector A is the same thing as this vector A. They both have the same direction, they both have the same length, and that's why they have the same name. I can draw vector A wherever I want to in the 4 quadrants. I really can. Right now they're both in quadrant 1, but I could have drawn it over here in quadrant 2 or 3 or 4. And it doesn't matter because you're not focused on where it is located so much as you are the length and the angle that it forms with an invisible horizontal. But a lot of people, just to make things like standardized, we like to shift our vector to the origin. I always ask my class, like, hey, if you've got a vector that's like random out in the middle of nowhere, I would like for you to shift it to the origin, because then math just becomes a lot easier. So let me give you an example. Let's take this vector down here. If we know that this is the point, let's say 2, 0, and we know that the terminal point is the point 5, 2, okay? If I wanted to shift this vector to the 0, it really is as easy as shifting this backwards 2 spaces, and therefore shifting this backwards 2 spaces, and then just asking yourself, okay, so where would that end up? Well, if I took this back 2 spots and this back 2 spots, then vector A would start here, and it would look kind of like that. I know that's not very straight, but I don't have a ruler, so sorry. So once it's shifted back, it's going to be the same length as it was before, and it's going to be the same angle that it was before, so it's still called vector A. It's just that now there is a new terminal point, right? Well, if this got kicked back 2 units, then this got kicked back 2 units, so it's now the point 3, 2. Now what I want you to notice is that I changed the notation of the coordinate point, and the reason for that is because any time your vector is at the origin, okay, so if the tail is at the origin, then that's called standard position, actually, of the vector. And you can just name the vector by its terminal point. So what I would say is, if I were in class, I'd have this A that's way up here, or this A that's down here, and I'd say, okay, let's shift A to the origin. Well, once you figure out how to move and count backwards and shift it, that new terminal point is how I would name it. So I would say vector A is equal to 3, 2. So I name it by its terminal point, and that's another thing about those brackets. They're called like chevrons or whatever, but anytime you see these chevrons, you can assume that if you see this, you'll be like, oh, the tail must be at the origin. So that's why nobody says 0, 0, because that's going to already be assumed if you see that notation. Okay, so if you see a point without that notation like this or this, you know that the vector's probably off in space somewhere. All right, so now let's get busy actually doing something with this, okay? We're going to talk about vectors that are not on a coordinate plane, and then we're going to talk about combining vectors that are not on a coordinate plane. So let's say that we have something similar to the A that was above, okay? And there is no frame of reference. We don't know this point. We don't know the terminal point, and our job is just to do something with it, you know? So like maybe this is vector W, and somebody says, okay, I want you to do 1/2 of W. Okay, so what that means is they want you to take W and make it half as long. They want you to apply, this is called a scalar. So a scalar is a number that changes the magnitude, okay? Scalar changes the magnitude. Remember, magnitude is just length. So I just need to draw this half as long. So 1/2 W would look like this. Now notice I drew it parallel to the one before it because you do not want to change the direction. You still want this angle right here, whatever that angle is with the horizontal, you still want it to be the same as that angle right there. So try to keep it at the same angle, which means make them parallel, and just draw it half as long, okay? So if I did like 3W, man, I don't have room for 3W. I would draw that 3 times as long. Another thing that you could do is you might see a negative W, and I'm going to do that in a different color just because, okay? If you saw a negative W, okay, that's interesting. A negative in the front is actually one of the few things that can change the direction. And it changes it to the complete opposite direction. So if W looked like this before and was heading, I guess that would be like northeast. Well, now it's not going to be heading northeast. Now it'll be the same length as it was before, but the arrowhead will be going southwest. So that just changes the arrowhead into the other direction. Okay, so those are some ways that you can sketch or deal with a vector that's out in the middle of nowhere. It's called be careful. You know, maybe even pull out a ruler or pull out a protractor if you like to be precise and perfectionistic. Obviously, I don't, as you can see in this video, but that's the idea of how you're supposed to deal with it, okay? Now, combining vectors, okay? Combining vectors, y'all, that's fancy talk for adding or subtracting vectors, okay? So when you see combining vectors, I mean, that's really all that we're going to do. Adding vectors. So whenever you have this is actually really kind of a cool deal, I'm not going to lie. I'm going to make up 2 vectors, okay? Let's call this vector W again, and then I'll take a different color, and maybe that's going to be vector V. Okay, so we don't know where they are in space. They're just random vectors in space. And we want to combine them. So somebody has asked us to do like W plus V, okay? Let's say that someone's asked for that. Well, if we're supposed to be adding W plus V, there's no numbers here to add together because we don't have any numbers. We just have a picture. And this addition of 2 vectors just means what would happen if this vector met up with this vector. This is when I like to think of them as a force or a wind or something like that. So, I mean, honestly, think of it that way. Think about a wind that's blowing this direction, and it's shorter, which makes it a little less powerful than this one right here, okay? And then this wind comes along, and they meet up with each other. You know, it's like, what's going to happen when the 2 winds meet up with each other? Well, they're going to create a new current, a new stream, and that new stream is going to be going a different direction, right? Like these are not, they're going to kind of come together and form a new angle, and they're going to come together and form a new magnitude. Now the way that you can do this, there's 2 ways. There's the triangle method, which the triangle method is whenever you put the vectors together head to tail. I'm going to write the directions first, then I'll show you. put together head to tail, and resultant is drawn head to head. So this is the rule. Put together head to tail, then resultant is drawn head to tail. Now the resultant, guys, is fancy talk for the answer, okay? The resultant is the resulting vector once these two vectors get together. And so what this would look like is the following. I'm going to redraw W like it was before, okay, except not because it's a little off. Okay, it's kind of more tilted. There we go. So here's W from before. Now instead of just drawing V way out in space here, I want these two vectors to touch, and I need to put them together head to tail. So somebody's head needs to touch somebody's tail. Well, I've got this guy's arrowhead right here, so I'm going to go ahead and take the tail of V, and I'm going to shift this green vector down to where the tail touches the head of this one, but I'm going to try to keep this one the same length and the same direction as it was before. So there is V. So there's my V and there's my W. So I have connected them head to tail. And now I draw a resultant vector. I'm going to draw that in red. The resultant vector is drawn head to head. So here's the head and here's the tail. I just connect the triangle. Whee! And that red vector right there, that is the answer to W plus V. So when these two winds or forces got together, what ends up happening is that the resulting wind is now just barely going southeast, and it's about, look at the length of that, it's somewhere in between the length of these two. So that's the triangle method. Alright, cool. That's what you'll use most of the time when you're in space. The next part of this video is about how to deal with vectors when you're on the coordinate plane, okay? Which a lot of people like more because there's numbers associated with it and formulas and stuff. So I will let you take a break because this is already a long video. Go take a break, get a drink of water, whatever. Also, go grab your calculator. You will need a calculator that has sine, cosines. You'll need those buttons, maybe tangent, you know. So go get your calculator and then come back when you're ready, and we will finish out with vectors on a coordinate plane. Okay, cool. So if you're back, you have your calculator. Now, I'm going to ramble a little bit while you're getting a chance to sketch the picture that I've already drawn here in this box. We're going to combine vectors on a coordinate plane. So once again, combining vectors means we're probably going to try to add these guys together. But I'm going to show you how once you're on a coordinate plane, it's a little bit different than the triangle method that I showed you whenever vectors are out in space, okay? What this is going to be is it's going to be something called a parallelogram method, where we draw a parallelogram instead of a triangle, and we can still find our resultant, okay? Now, step one, okay, once you finish drawing this, pause me if you need to, but once you're finished drawing, step one is you want both vectors at the origin. Now, notice blue over here, old blue, is already at the origin, and in fact, it's obvious because it looks like it, but also because I use chevrons to name the terminal point. So if I use that symbol, it means that the tail is already at the origin. So that's what this guy's name is. And this red one over here is not at the origin. Now I've labeled both points, the terminal point and the initial point. But what we need to do is move it to the origin first. So the way that you could do that is just kind of count backwards, right? If this is at the point 2, -1, then I need to go up 1 and backwards 2. So if I go up 1 and backwards 2, then I need to take this point and go up 1 and backwards 2, and then I need to draw where it's going to end up. So either count it out and redraw it, or another little trick that I kind of hadn't shown y'all yet, but another little trick for shifting to the origin, and I'll write it right here, shifting to origin. If you don't like picking it up and counting it, you could always do head minus tail. And if you just subtract the terminal point minus the initial point, you'll get where it's going to end up, okay? So the head, so basically this is the head, and I'm going to subtract whatever the tail is. X with X, Y with Y, guys, okay? Combine like terms. So 5 minus 2 is 3. And then -2 minus -1, that should be a -1. So that right there is your answer of where it will end up. So 3, -1, 1, 2, 3, -1. I'll put the arrowhead at 3, -1. I will draw the vector to the origin. And now this is the vector I want to deal with. Okay, notice it's the same size as this one. It's at the same angle as this one. It's just kicked back to where its tail is at the origin. That's how you want to start the problem. Okay, and this is just another little formula to help you do that. Now, once you have this, I told y'all there would be some kind of parallelogram method involved, and that is true, but I'm going to show you the math arithmetic way because, oh my gosh, you're going to love it. Now let's give these a name just so we have some notation. So whatever letter you want to call this, let's call this one A, I guess, and let's call this vector B. So if we were asked to find A plus B, then what we would do is we would sketch a parallelogram, and then we would draw the diagonal of the parallelogram. That's the second method for finding a resultant. But an easier way than the geometry is if you have numbers, use the numbers. And we do have numbers now. We have A has this terminal point, and B has this terminal point, and this is telling me to add them together, so why not just add them together? So I'm going to do the x of this one plus the x of this one. So what is -2 plus 3? Well, -2 plus 3 is 1. And then what is the y plus the y? So 4 plus -1 would be a 3. So the terminal point of the resultant is going to be 1, 3. And that right there, that green vector right in between those two, is going to be my actual answer, okay? And so that's pretty cool. So, and I'll just to prove to you that the geometry works, if I had drawn a parallelogram out of A and B, remember a parallelogram has parallel sides here and here? So if I had drawn a parallelogram so that those are parallel and that the B and this one are parallel, this is the diagonal of that parallelogram. So this is the other option to doing the triangle method that I showed you on the other page, is to stick them together tail to tail, draw a parallelogram, and then draw your diagonal coming out from the middle. So there's your two methods. But anyways, that is combining origins on a coordinate plane. Lots easier because once you have their terminal points, whatever math it tells you to do, you do it to the point, okay? Just remember to keep x with x and y with y. So what about applying a scalar on a coordinate plane, okay? Well, applying a scalar is actually easier than what we just did. Applying a scalar would be like if I had 1, 2, 3, 1, 2. Let's say that I have this vector right here. Okay, so this is the vector 3, 2. And if the vector 3, 2 has been drawn and somebody asks me, okay, then I want you, let's give it a name W, I want you to do -3W. Okay, if I'm asked to do -3W, on the other page we talked about the fact that the 3 would make it 3 times longer, and we talked about the fact that the negative would make it go in the opposite direction. So you can try to measure it out and figure that out on your own, or we can just take the point for W and multiply it by the -3. So -3 times 3 is -9. -3 times 2 is -6. This is where the vector is going to end up. So -9, 1, oh gosh, this is going to be hard. 1, 2, 3, 4, 5, 6, 7, 8, 9. -6, 1, 2, 3, 4, 5, 6. So somewhere over here is going to be where we end up. I should have thought ahead and not put that math in that quadrant, but whatever, it happened. Get over it. Okay, so the blue vector is -3W now. Notice it's 3 times as long and it's going in the opposite direction, but by using algebra, or rather arithmetic, we can get the answer way quicker. So yay! I love being on a coordinate plane. You're really just doing basic math to your x's and your y's. This is the grand finale though. This is awesome. These are my favorites. And when I taught pre-AP pre-cal, you bet your butt that the end of every test was at least one or two of these kinds of problems, okay, the real world situation. So let me give you a chance to read it while I'm looking at it as well. Okay, so if you've read it, I mean, I know you don't know how to do it yet, but here's the idea. You've got a plane and a really strong wind comes along. So you probably already figured this out, but you know, a pilot's going to have to, it's kind of like driving a car. I mean, you have to adjust the car or adjust the plane to fight the wind. And if you didn't, then the plane or the car would be pushed in a different direction. So imagine driving down the highway, a wind comes along and you don't touch the steering wheel. Well, you might drive into the ditch. That's what's happening to the plane in the sky. This wind is pushing the plane, and we're going to find out where it pushes the plane. All right? So to do that, you have, it's the same stuff that we did above. What we're going to do is create a vector for the plane and a vector for the wind, and then we are going to combine them. So to find the components of the airplane, okay, the first thing that you would do, I'm going to leave this for math and I'm going to draw the picture up here, I guess. Okay, so I'm going to draw a coordinate plane, and I need to draw these in the right place. So the plane, I'm going to do the plane in green. And he is going 510 miles per hour. Okay, in a word problem, the speed is the magnitude or the length, okay? And here's our direction, 15 degrees north of west. Okay, so north of west. So where's the west? The west is over here, and I need to go 15 degrees north of that. So here's my 15 degrees north of west. So I'm going to draw a vector right here, and I'm going to draw it pretty long because it's 510 miles per hour. Now notice I'm not going to scale my axis, because who wants to try to do that and go along with this 510? Not me. So I'm just going to draw without a scale. All right, now let's draw the wind and blue. Does that make sense? Sky blue wind. Okay, the wind is 45 miles per hour, so there's its magnitude, and it's heading due south. So due south, you know, this is the south, so it's just going to start at the origin and go straight down. It's going to be little, right? It needs to be little because 45 related to 510, you know, that's only like a tenth of the size. So it needs to be a baby vector. All right, so let's label him 45. Okay, so now that we have the picture, we need to find the components. Okay, guys, the components are just the x and the y. Oh, and I need to switch back to green now. Okay, the components is just the x, y. That's what that word means, is let's figure out what point makes up the terminal point, okay? Now, how are you going to find that is the question, because that you know that this whole thing is 510, but we're not sure what the x and y are. So we're trying to find how many over do we need to go, and then how many up do we need to go. Now once you sort of draw that movement, some of you already know exactly what to do. This is very familiar. It's like the last 2 or 3 weeks. We have a right triangle, you have an angle, you have your hypotenuse. Why not find the x and the y? So this is why you need your calculator. You're going to run some kind of a SOHCAHTOA formula, okay? So let's see, if we want, let's say that we want the x. If we want the x, it's the adjacent. Or you could just go with the fact that we learned that the cosine is equal to, do y'all remember how we did, you know, cosine is either opposite over, that's not a 0. Hold on, let me erase that. Yeah, you know what, I am going to do that. Sorry, hold on. I'm going to keep what I was doing. Okay, cosine is adjacent over hypotenuse, okay, or it's the x over the r. We talked about both of those over the last couple of weeks, so use either formula that you want. I'm going to go with x over r, just because I've got an x staring at me and I've got an r staring at me. And I know the angle for this one, so the cosine of 15 is equal to x over 510. So whenever you go to solve for x, maybe multiply both sides by 510. And that's going to be our answer. Now, you're going to have to be careful because when you type this in on the calculator, it's going to give you a positive number. But guys, please keep in mind that you're in this quadrant, and in this quadrant, the x needs to be negative. So let's type that in and see what happens. I think you're going to have to change it into degrees as well. So if we are here, we're going to do the cosine of 15 times that 510. Okay, I'm getting negative 492.6. Negative 492.6. That's what I am getting for my x value. Okay, now I'm not going to write out everything for my y, but here's what's pretty stinking awesome. As long as the angle in question goes with the x-axis, like it does in our picture, see how this is connected to the x-axis? This formula is going to work every single time. Like, in other words, x is always going to be whatever the magnitude is, the magnitude of your vector. So I'll write magnitude of the vector times the cosine of the angle, as long as the angle goes with the x-axis. So you might want to make a little side note there, okay? If you drew something to the y-axis, don't use that one. You better find what it is to the x-axis first. But it's the magnitude times the cosine of the angle. If we did SOHCAHTOA again to find our y, guess what? It's going to be the same dang thing, except we won't be dealing with cosine because y is opposite the angle. We'll be dealing with sine. So it'll be like the magnitude of the vector times the sine of the angle. So I know it looks like I'm putting the word magnitude in absolute value bars, but that's just because it's always going to be positive, and because the notation for magnitude that I showed you in the other page, it's the absolute value bar. So anyways, magnitude times the sine and magnitude times the cosine. So that being said, let's go ahead and quickly do the y here. For this problem, it would be 510 times the sine of 15. So let's type that in. And 510 sine 15, it would be 131. Okay, so since it's a 0.997, I'm just going to call that 132. Now, can the 132 stay positive, or do I need to turn it negative? Well, it stays positive because we're in quadrant 2, and the y is positive in quadrant 2. So these are my planes components. Now, we're quickly going to do the winds components because we're going to use these two formulas up here, okay? So for the wind, okay, we need the magnitude, which is 45, times the cosine of the angle, and 45 times the sine of the angle. Now I left the angle blank because I want you to tell me what is the angle. Well, it's on an axis, and you're thinking, I don't see a triangle, I don't know what angle to use. I get that, but guys, we know our unit circle, so why don't we use that angle? Start in the east and go all the way around, and what angle is that? Well, it should be 270 from our unit circle. So if the triangle doesn't form, if you're on an axis, you can always just think unit circle, okay? And you're going to type these in the calculator, and when you do so, you should get 0 and negative 45. And honestly, if you looked at that, that point makes sense because we're just on a coordinate plane, so you didn't really need to run that formula for this problem, but we did it just to practice, and I wanted you to see that the formula is going to work even if you can just glance at it and figure it out. Okay, so now what? So now we need to combine the components. Well, we have two terminal points, so to combine the plane plus the wind, all we have to do is add these together. So let's do that. Let's add this x plus this x, and it looks like it's just that. And then we're going to add 132 and negative 45, and I am getting 87. Okay, so this is our new, our actual plane components. So this is where it has been blown by the wind. This is where the wind has blown it. So once you have the new components, you can do all kinds of stuff. You can find the new speed and magnitude, you can find the new direction, and then decide if it was a headwind or a tailwind, which I'll tell you what that is in a second. This is easier than you think, okay? For the new speed or magnitude, remember this just means the length, guys. And if you need the length of a segment, you could totally do, well, I would do Pythagorean theorem or the distance formula, either one. If this is the x, okay, the x is negative 492, so that's negative 492.6, and the y is 87, then can't you find that new length of that vector? You sure can. It's just the hypotenuse. So grab a calculator. We're going to do negative 492.6 squared plus 87 squared equals c squared, and we're going to figure out c. So I'm going to shut up and just punch some buttons, and let's see if we all punch the same buttons. Oh, I think it's 492. I went a little dyslexic there. There we go. 492.6 squared plus 87 squared. Okay, I'm getting 500.2 for the length. So remember, this was a word problem, and what was that, or how should I label that, you know? This is the speed of the plane, so it was miles per hour. Now I'm going to go ahead and jump over and answer this question. What was the plane doing? The plane went from, it was originally 510 miles per hour, and now the new speed is 500 miles per hour. So it slowed down, right? And any time you slow down, it is a headwind. Because think about it as like you're walking down the street, a wind blows against your head, it's going to slow you down. But if a wind hits you in the tail, it's going to speed you up. Okay, so a headwind is if you slow down. All right, cool. So now what about the new direction? Well, the new direction, guys, is just the angle. So take our same picture from this box and let's look at how would we find this angle in this corner right here. You know, how would we do that angle? Well, just SOHCAHTOA stuff, you know? I mean, that's really all it is. You know the y, you know the x, and that would be the opposite and the adjacent, so I'd probably just use tangent. So the tangent of that mystery angle is the opposite over the adjacent. And you probably don't even need the negative there. You know what? In fact, I'm going to say just put that in absolute value bars. We don't really need the negative. And then let's do, I guess we would type in second tangent of 87 divided by 492.6. And we are going to get 10 degrees. Now that 10 degrees, that's not the final answer, because if I just said, hey guys, the plane's going 10 degrees, you would be like, 10 degrees what? So we need like north, south, east, west stuff. So let's look at our picture. It is 10 degrees north of west because it's up from the west axis. Okay, so that's how we would answer it. Now I know this is like the longest video in the history of everything, but it covered a lot, and it, you know, hopefully you took breaks if you needed them. Go try some homework problems, and the solutions video will probably also be a good 15 minutes long. Just gonna warn you. All right, guys, good luck, and let me know if you have questions.